Well, welcome. So today I want to continue right where we left off, discussing temperature and volume graphs. So just as a quick refresher, you'll remember that what we did last time is we plotted a phase diagram or a state diagram, which is two properties, and we chose to start with those two properties of temperature and specific volume. And we discussed how you plotted isobars on this graph, and we ended up with a shape that looked something like this. Okay? And here at the top was what we call the critical point, or CP for short. Alright? We've also done this now in lab. So we've dealt with this and we've been able to see a practical example of how this plays out. You'll remember that over here we had liquid, over here we had vapor, and right here was a mixed region. So we had liquid and vapor. And across our graph, we had running all of these isobars. So this is probably the fourth or fifth time you've seen this now, because we also have been doing it in our Zoom meetings. However, I really want you to get this, because today the story is about to get a little more complicated, all right? So this blue line I'll just label as an isobar. That's what they are. Isobar meaning constant pressure, bar for pressure. So this is where we came from. Today we're going to do this same thing, only look at the pressure graph. So as you can imagine, it looks very similar. So this time my y-axis is pressure, my x-axis is still specific volume. And I'm going to build this up the way we built that up, all right? If you remember what we did, is we chose a point, say starting here, and we said as we increase the specific volume, what's going to happen to the system? And we discovered that the temperature goes up. And that's why on the temperature versus volume graph, we started at a point like this, and we said our isobar is going to go that way. Volume and temperature are going to increase together. It turns out that on the pressure versus volume graph, it's just a little bit different. It goes that way. Okay? So what this means is that as we increase the volume, the pressure goes down, right? That direction of the arrow makes sense. And this is intuitive to us, all right? If I have a container with a specific amount of gas and that gas is not changing and our temperature isn't changing, the only thing I'm going to change now is make it bigger, increase the volume, so go this way, right? This is what I'm doing. That's supposed to be an arrow. I have a little arrow, a little increase in the volume direction. Then it's intuitive to us that the pressure drops. As we make it a bigger and bigger volume, the pressure is going to go down. And so this arrow right here is decreasing. It's got a negative slope. So if I do this over and over again, I do get the same plateau where my phase transition is, and then I go down again. So this should be reminiscent of that blue isobar. See, it's almost the same story, only these are going downward, okay? So again, I do the same thing, and I build these up and build them up. And let me actually erase this and do it in blue. So we've got one isobar that looks like that. Isotherm, because now this is a constant temperature line, all right? So we have to make that distinction. Here, pressure's graphed on our axis. So what we're talking about is as we change the system at a constant temperature. So this is called an isotherm. All right? And so an isotherm, it means that every point, every single state that's along this line is always at the same temperature. And if I draw the rest of them, we get the same type of behavior. And if I drew this right, I can connect up, and I drew this bottom one a little bit shallow. And I get the same type of graph, okay? So the general shape is the same. It arches up, and I have these isotherms coming across. The only thing I want you to remember is that when I'm off to the side here, instead of a positive slope angling up, I have a negative slope coming down. I also still have, do this in black, and I still have my critical point up here, all right? So take a minute to compare those two. Same regions too, liquid and vapor. Over here is liquid, over here is vapor. These two graphs and what their similarities and what their differences are, okay? The next thing that I want to talk about is moving on from just dealing with liquid on one side, mixed state, and vapor on the other side. That's all we've done, right? Crossing from liquid into vapor. Because now I want to deal with solids. Where do solids go on these diagrams? Well, we know that solids are more dense than liquids. And so, in general, right, we're going to get to that, but in general, they're more dense than liquids, and so we go that way to deal with solids, right? On our volume, specific volume axis, we're going to be decreasing the specific volume. And I'm sorry, I don't know what I said. Solids are more dense, and specific volume and density are inverses of each other. So as solids become more dense, they have a lower specific volume. Okay, that's what I'm meaning to be saying here. So this side of our chart deals with solids. And so let's go over back to this one that we're used to, temperature versus volume. We've got this region right here where liquid transitions into solid. All right, so this is liquid in here. But now over here, let me just write this as liquid in here. This is still liquid, but now over here we have solid. And then of course there's a transition period, right? So we saw how liquid had to cross through this mixed region to get to vapor. We had a region where there was a transition happening in between. That's the same with this. There is a region. So it's liquid on this side, it's solid over here, and there's this strip in between, which is both solid and liquid. And I hope you can read my vertical writing, okay? So this is how we incorporate solids onto our graph. Now you may notice I left the bottoms out here. Where does this go? What's down here? Well, turns out that there's a line right here that divides off everything else, and everything below that line is solid and vapor. And at first that may seem weird. How can something be in a partial phase of solid and vapor? Doesn't it have to go through liquid first? Not really. Generally this occurs at lower pressures than we're used to, so we don't deal with it all that much. But in your brain you can probably recollect thinking or seeing a situation where you had a solid and it vaporized. It doesn't necessarily have to go through the liquid phase. So all of this is solid right here, that's all solid. And remember that all of this is vapor over here. And so it can go right from solid to vapor. So down here, this is the transition period between solid and vapor. So this diagram got a little more complicated, but I hope we're still understanding what's happening. The phase of a system is given by a point on this diagram. What phase are we in right now? And then to cross between phases, we always have to pass through an intermediate point or a barrier point. Okay? So from liquid to vapor, we cross through the liquid and vapor region. From liquid to solid, we cross through the solid and liquid region. And from solid to vapor, or back and forth, it's vice versa on all these. From solid to vapor, we cross through the solid to vapor region. All right? Same thing happens on the pressure graph. So I'm just gonna drop that in messily. All right, it's really messy. That one's a nicer one, but it's the same basic shape and it's the same basic regions. All right. Now, what you'll notice on this graph is that there's this line. And that line, I tried to draw a little bit thicker because it's a special line. On this side, we can have substances that are liquids and vapors. On this side, we can have substances that are solids and vapors. Okay? So vapor could be on both sides. But if you're right on this line, right, any point that falls right on that line, you'll notice that it's touching solid, liquid, and vapor regions. So if your state is right on that line, you can be in any of those three regions. And because there's three phases that are all coexistent, this is called a triple line. Okay? So you can literally have a substance that some of it is solid, some of it is liquid, and some of it is vapor. Okay, so the next thing I want to talk about is what do we do for substances like water that I mentioned a little bit earlier we were going to come back to that do get less dense when they freeze. Remember how we motivated the solid region? We said that the density goes up once we freeze it. Well, what if the density actually goes down? That means that instead of moving this way on our diagram, we need to move this way. And so here's what that looks like. I'm going to draw a new diagram. So here are my axes, and I can do pressure or temperature. I'm going to do pressure, all right? Here is the shape that we're familiar with, and our triple line across the bottom. So on these diagrams, what happens is this comes out a little bit further, and our region does something like this. And you can imagine those as being straight lines. I'm not an artist, okay? So before, if we were sitting here in the corner of this region, here in the corner, to go to solid, we have to go that way. But here, if we're here in the corner, we can actually still come this way and still be in the solid surface. You'll understand this better as we continue, not necessarily today, okay? I apologize, there's just too much to get to, all right? So if you leave the lecture today a little bit muddy about this distinction, that's okay, all right? There's a couple important things that I want you to understand that don't necessarily have to do with the chart, all right, if you're struggling with the chart. First of all, water does this in contrast with almost every other substance that we know. I say almost because there's a slight few that do it along with water. But a tiny, tiny percentage actually do this. And remember, what we're talking about is contracting or expanding on freezing. So this, I'm going to write over here. This is a substance which contracts on freezing. And I don't mean freezing in a colloquial sense, I mean it as a technical scientific definition. Remember, on our chart, freezing is the technical term for crossing over from the liquid across the barrier into the solid region. That's what I mean when I say freezing. I mean it in a technical sense. So contracts on freezing, and this is almost everything. This one over here is a substance that expands on freezing. And this is water and buddies. So it's got a few friends that also expand on freezing, but mostly it's just water. Okay, this is a big one. And so it's sort of interesting. There are chemical reasons for this. It has to do with how the hydrogen bonds are structured within the lattice of liquid water. That is a story for a different class than this, but essentially water is very, very unique And so it's interesting that so much organic and biological life depends on water. It's got this very special property that other liquids don't have. All right? So again, we're going to come back to what this actually means for this line, for this wall, this barrier here to be shifted over, not to be where you'd think it should be. But for now, I just want you to understand this is that there's a slight difference between these two in terms of where this solid liquid buffer zone, the part where it's mixed solid and liquid, where does that fall along the volume axis? Okay. The last thing that we have to go over is a chart that I wish I could show you in 3D. All right. How this would be best learned is for me to have a model here and to have all of you here, and I could show you the model and we could touch it and actually see it and visualize it. But I've tried to do my best with drawing it. So for right now, just look at the blue and I'll explain what the black charts are later. All right. So this is a PVT surface. It's the 3D version of those 2D graphs we've been looking at. Remember that we have all three variables. We have pressure, specific volume, and temperature. And up until this, we've only been looking at two at a time because that's all that we can fit on a two-dimensional XY axis. This is in 3D. It's a 3D XYZ plot, and it shows a surface that has pressure, volume, and temperature. So it's like a mathematical graph still, with pressure increasing going along this axis, volume increasing along this axis, and temperature increasing along that axis. And I've marked out what these different areas look like. Imagine this is a 3D thing, something that you could hold in real life. All right. First of all, here's our liquid vapor region. And we still recognize that one side of it is vapor. Oh, and I didn't write liquid on here. All right. One side of this is vapor and one side of it's liquid. This is what we're familiar with, right? From liquid to vapor or back, and it crosses a buffer region. That was along an isotherm. So I want to draw an isotherm on here. An isotherm is a line of constant temperature. So it would be something like this on the temperature axis, right? I would pick a temperature and I would slice through the entire surface along that line, right? It's like I'm going to take a knife and I'm going to go in and slice it along that temperature. So what does it look like? Well, it goes up through here, and it curves up, and it crossed, up, and it crossed, up, and it crossed. So I think I drew that fairly okay. Do you see how with that green line, I took a knife and I sliced into this diagram at a constant temperature? And I could do the same thing. I could do one here, or down here. All those green marks, I can do slices through the diagram. Those are the isotherms that we've been looking at. Likewise, isobars, which we looked at the first week, those are slices along this axis, okay? I'm not going to draw any, but it's like slicing the graph this way, okay? Slicing it height-wise. And looking at where does that slice fall along each thing. So these are our regions that we're familiar with. Then we come out to what we learned today, the solid and liquid buffer zone. And this one that I've drawn is for almost all substances, not water. Okay, this is a substance that contracts on freezing, not expands. Over here we have a solid zone. Down here we have our solid and vapor zone. And here is our triple line, okay, where we have liquid, solid, and vapor. So from this is the real structure, the real underlying structure that we've been looking at. And you can see how from this we've gotten our three different graphs. So check this out, I think this is cool. Imagine that I am looking from this perspective. Imagine this is a 3D model and I come down here and I look up at it like this. What I'm going to see is pressure on one axis and volume on the other axis. So to me right here it looks like there's a plot of pressure versus volume. And that's what this is, right? We've talked about this plot, pressure versus volume, and this is what it looks like. So that should be familiar from the board that I just pushed up that you can't see. This is what it looks like if you look end on, coming this way. Now, if I get up on a chair, which I'm actually going to do to illustrate the point, and I look down like this, I'm looking from a top view on the graph. This is my perspective, okay? Then what I see is temperature increasing this way. I have it drawn here, but it's that direction. I could have drawn it back in this corner along that axis, right? So that's the temperature axis and the volume. So this is what we learned about last week, right? Temperature and volume. And again, we see the familiar looking plot right here, okay? So you can imagine that's what it looks like from above, looking down. And the third view is a new one that we haven't talked about yet, but that's how we're going to end out. And that's if I get down here and I look this way, up at the graph this way, all right? Now that one looks a little bit different. You can sort of see how we get that arching shape and everything, no matter if we look from this way or from that way. But if we're over here, we don't quite see that. We see something else, and I want to draw a couple more isotherms actually to illustrate kind of what we see. So this one's going to go up to the critical point. I don't exactly know how to draw it. Okay, and this one's going to go straight up like that. So you can see that we've got this surface here. It's a curvy sort of, it's smooth. It's not like rough or jagged or anything, but it's sort of weird how it warps in and out. And if we look at it from this perspective, we get this graph. I'm staying on this side, okay? Pressure is increasing on this axis, and temperature is increasing along that axis. I hope you can see how that graph comes from looking at this graph. And here we have our critical point. That's way out here. Okay? Here is the triple line, which is a line, sure, but from the angle we're looking at it, we're seeing that line like this turned on its end. We're only seeing the very end of that line. Okay? And so this is just a point from that view. And so sometimes it's also called the triple point. Don't let that confuse you. The triple line is the triple point. People just call it the triple point because from this view, it looks like a point. From these two views, it looks like a line. So they mean the same thing. And we can label our regions, right? So this region down here is vapor. This region in the middle is liquid, because we're seeing this wall back here, right? That side wall of it, that's what we're seeing. And this region out here is solid, because we're seeing this wall coming up here, okay? So this is the PT diagram, where we've eliminated volume. And again, I've talked to a lot of you guys about the fact that beyond this critical point, it's sort of an unintuitive phase of matter. It's not like something that we would readily recognize. And that's sort of seen from this graph by the fact that it just ends. There are these nice dividing lines, and this one goes forever this way. Solid and liquid are completely divided on for forever. But this liquid and vapor, that goes up to a point and then dead stops. And past this point, what's out here, that's sort of this weird blur of solid and liquid that's not quite either one, but it's kind of both. just sort of weird. So there's a lot to digest here, and we're going to keep talking about this in future lectures and classes. But if you need to go back at all, this is one that I would go back and pause and just stare at the pictures and think about what the heck is going on. Okay? So, thank you guys.